Hello, all. Hope you're doing well. So, I wanted to start this lecture with this screen because by mistake I have written classification of acids, but it should be salts. So, I am rectifying that. So, we are going to start the next lecture of acid, bases, and salts. So, we'll be discussing about commercial salts little bit, not in depth, about basic reactions which are happening commercially when we try to obtain industrially. So what reactions we are following, but it's not core industrial process that we are going to discuss in this video. So before that, we are going to discuss about solubility of salts. So this is very generic since solubility of salts is going to vary in water. Obviously this is with respect to the solvent that we are taking is water. So when we add salt in a water, so there are different type of you can say actions that we observe. So sometimes the solubility is quite high that we dissolve in like salt in water. So if we stir it or even if we don't, so it can solubilize. So its solubility is quite high. At room temperature it can happen. So we always take a standard. So when it comes to water, so we say solubility of a particular substance or of a salt which can be dissolved, the maximum amount of any salt that can be dissolved in 100 ml of water at a particular temperature. That is how we define solubility. That's in general. So we can just write. So solubility is defined as the maximum amount of salt that can be dissolved at a particular temperature because temperature plays an important role when it comes to solubility. In 100 ml of water which is acting as a solvent over here. Details of solubility I'll be discussing in one of the lectures that I'll be starting, like that will be later on, not right now. Like matter in our surroundings I'll be starting soon. Is matter around us pure? That will be discussing later on. So that in that second chapter we'll be discussing about solubility in depth. So there are various things: solubility of solids in liquids, then we have gases in liquids. That's a very important topic. So over here what we are going to discuss is, let's say if we have a salt is very much soluble. This is very generic statement. If more than 1 gram of it can be dissolved in 100 ml of water. So if more than 1, that means it's soluble. Now if it is let's say insoluble, if not more than 0.1 gram of salt can be dissolved in same 100 ml of water. Now this is insoluble, this is soluble category. Then the third category we can say slightly soluble. We even say sparingly soluble, slightly soluble. So when we have a range in between this 0.1 gram to 1 gram of salt which can be dissolved in 100 ml of water. So this is sparingly or slightly soluble. Now let's try to generalize so that we can understand which kind of salts are soluble in water. So we have soluble in water, insoluble in water. So when we say soluble, we say all nitrates. Nitrates means metal nitrates. Nitrate is NO3 minus ion. So sodium nitrate, potassium nitrate, any kind of nitrates. And nitrites. These are soluble. Nitrites are NO2 minus. Sodium nitrite, magnesium nitrite, calcium nitrite. These are soluble. This is one category. Then all chlorates are soluble. Now what are chlorates? Chlorates are ClO3 minus ion. Metal chlorates are soluble. Every kind of chlorates that we know. Then all chlorides Cl minus are soluble. Now we do have exceptions over here. If you remember AgCl, so except silver salts like silver chlorides. So AgCl, we have Hg2Cl2, we have PbCl2, and so many others are there. So let's take these examples only. And PbCl2 is very much soluble in hot water. Do remember one thing, solubility can vary. It depends upon the temperature. I have written in the definition. So if it's depending upon the temperature, that means at a particular temperature, the solubility can be low. At the same time, if we increase the temperature, solubility can be higher also. Now it depends upon the salt category, what kind of salts we are talking in question. Then all sulfates are soluble. Now sulfates are SO4 minus. These are soluble except CaSO4, calcium sulfate, lead sulfate, PbSO4, Hg2SO4, Ag2SO4. These are there. Then all the salts of cations, ammonium, sodium and potassium. These are soluble. Acetates are soluble. Sodium acetate, potassium acetate, right? So acetates are soluble. So these are all categories of soluble salts that we can think of. Then coming to insoluble. Now all carbonates are soluble except those of alkali. Sorry, my mistake. All carbonates are insoluble. So except ammonium carbonate, and those of alkali metals, right? Then we go to next, all sulfides. Sulfides are S2 minus, are soluble. Again, I have said soluble, it's insoluble because we are discussing insoluble only. So these are insoluble except alkali and alkaline earth metals. Now alkali metals are group 1, lithium, sodium, potassium. I have discussed many times in my previous videos also. Alkaline earth metals are group 2, beryllium, magnesium, calcium and so on. Then all hydroxides are insoluble except alkali, and some alkaline earth metals. Not all. So this was a brief category of most of the, you can say, salts which can be solubilized or not. Then we go to the commercial salts. Now, most of the salts that we are going to discuss, they are obtained from sodium chloride. Sodium chloride is also called as common salt, table salt. So we have, let's say, around 2.7 to 2.9 percentage of NaCl in seawater. So this is, you can say we have a lot of salt, if we say this NaCl in seawater. So if we want to manufacture other compounds from it, so why not? We can do it. So it acts as a raw material for various kind of, you can say, substances in our daily use. So one by one we are going to discuss. So, or we can actually say not commercial salts, because not all of them are commercial salts. Most of them are, but only one example is not a salt. So we can say chemicals obtained from sodium chloride, NaCl, right? Commercially. So the very first that we are going to discuss is sodium hydroxide, NaOH. Now this is also called as commonly caustic soda. Now if we talk about the commercial method, we call it as chlor-alkali process for obtaining sodium hydroxide commercially. So it's the commercial method of production. Now how do we do it? So what raw materials we are going to take? We are going to take brine solution. Now aqueous solution of NaCl is called as brine solution. So it's nothing like NaCl in water, it's a common name. If you take NaCl in water, so it's collectively we call it as brine solution commercially. So if we give electric current, then we will get NaOH, chlorine, and hydrogen gas. So this is aqueous, this is liquid. So we can balance this. This is aqueous again. Chlorine is gas, hydrogen is gas. Now chlorine being an ion, Cl minus will be, so being an ion, it will be obtained at anode, and hydrogen at cathode. So cathode is a negatively charged potential, H plus being cations will be moving towards cathode. So Cl minus is an ion, anode is positively charged anode, so obviously they will be attracted towards anode. So sodium hydroxide will be obtained slightly near to cathode, not exactly at cathode. Now, if we say these are all products, hydrogen, chlorine, sodium hydroxide, these are commercially important. Now, if we try to understand the uses of hydrogen, so it can act as a fuel. It can act as a, you can say, as a raw material for manufacturing ammonia. Ammonia is a very important, you can say, important raw material for fertilizers. Then if we say chlorine is very much useful for water treatment plant, then swimming pools, and even for manufacturing PVC. PVC is polyvinyl chloride. It's a kind of plastic. So we have disinfectants also where chlorine is there. CFCs, chlorofluorocarbons, pesticides. So chlorine has a very important aspect when it comes to commercial daily life products. Then we come to sodium hydroxide. It's a base. So where do we use base? We use base in the form of soaps, we have discussed before, detergents, even for paper making we use sodium hydroxides, artificial fibers also. Now if you mix this sodium hydroxide and chlorine, you can actually get bleach out of it. So which is used for bleaching fabric, for household bleaches, for cleaning purposes, so many uses are there. Then if we combine hydrogen and chlorine, we will get HCl. So hydrochloric acid is used in preparation of ammonium chloride. HCl plus ammonia gives you NH4Cl, ammonium chloride for medicines, for cleaning steel. So many uses are there. So this is not just one reaction. You can say it's giving us products which are used commercially and it's very much in demand. Then we go to the next one. That is bleaching powder. So chemically, if we say we represent bleaching powder with the formula CaOCl2, I've discussed in my previous videos many times, even in oxidation number. So CaOCl2, calcium oxychloride. So how do we obtain this? So we are going to take the raw material calcium hydroxide and chlorine. See, indirectly why NaCl is important, we'll discuss that part. NaCl is giving us chlorine. Chlorine is used over here in this reaction to give us bleaching powder, that is calcium oxychloride, and water is formed over here. So calcium hydroxide is also called as slake lime, and this is our bleaching powder. So actual composition of bleaching powder is quite complex. It's a mixture. It's not actually a compound, but the major component will be this one, because you have many things in bleaching powder. There are some agents which make sure the powder doesn't absorb moisture from the surroundings. So many aspects are there. So it's not only one component. And we use a commercial plant where bleaching powder is manufactured, that is Hazen-Clever plant. We never call it as Clever, it's Hazen-Clever plant. We write Clever, that's okay, right? Then we go to the uses of bleaching powder, which we know a lot. So it's used in the manufacture of chloroform. Chloroform is CHCl3. It's used in laundry for bleaching wash clothes. It's a very good oxidizing agent in chemical industries. Disinfecting water we discussed before. Then even just to make wool unshrinkable, right? Then so that it should not shrink. Then for bleaching wood, pulp and paper factories, right? For washing clothes in laundry, textile industry, they love bleaching powder, right? So then we go to the next one. So I didn't write uses in depth, but uses is something that you have to learn. You just need to know. So remember the reactions. Then we go to baking soda. So baking soda is basically what? That is sodium bicarbonate. Sodium bicarbonate is NaHCO3. So we have two methods to obtain baking soda. One is commercial. So first we are going to discuss laboratory. So how can we obtain laboratory, like lab method? See, it's not always that the same method that you're using in the lab, you can use the same method commercially also. Sometimes there are certain shortcomings that people have to see on the larger scale, this raw material might be expensive or this process might not work well. So the process that is working well in the labs might not work commercially. So they have to think any other method, any other pathway where they can obtain the same product at a lesser expense, less time consumption, less laborious. So many factors they have to look into. So in the laboratory, we can take sodium carbonate. This is also called as soda ash. Soda ash is like, you can say without water. It's a common name. So if we take sodium carbonate, obviously we have to take water, and if we give excess of carbon dioxide, we saturate the solution of sodium carbonate dissolved in water with carbon dioxide. So we will get our single product, sodium bicarbonate, in the form of precipitates. Now this is this precipitate can be separated, can be washed, dried without heating. So it's very easy if you want lesser amount of sample. Now if we come to the commercial scale, then we use this famous process, that is solvay process. We even call it as ammonia soda process. Now over here we will get sodium bicarbonate as an intermediate product. We even use the same method, solvay process, for washing soda manufacture also. Washing soda is sodium bicarbonate, decahydrate. So now what we are going to do, we are going to take our again same brine solution. See, it's very important, again it's used up over here. And we are going to take carbon dioxide and ammonia. So ammonia is a twisted reactant over here, which we never used in lab. So these all reagents are going to react and will give you ammonium chloride, which is aqueous, and sodium bicarbonate, which is in the solid form because it's precipitate. So now in this, ammonium chloride is formed, which is not required over here, but we can actually decompose to get ammonia, which is our reactant, and we can regenerate it, and HCl is formed. HCl is again can be used for the uses that we were doing previously on the reaction of hydrogen and chlorine. So when it comes to commercial scale, we have to think of how we can whatever secondary or byproducts we are getting, how we can use it, how we can you can say earn money out of it, or how we can reuse it, because we have to save all the, you can say, byproducts, all the waste. We have to utilize that in zero wastage. That is the best process that we can have. But yes, every industry has some shortcomings, but the waste should be minimum. That should be the goal. So now I have shown this one reaction in just one single reaction, but it doesn't happen like this. It happens in steps. The step reactions I haven't written, but otherwise these are the, you can say, the raw materials that we have taken, all these 4 reactants, and then these products we are getting. So we are going in short form. But yes, in the future we can discuss these commercial scales someday when we are done with all the, you can say, chapters, whatever my goals are there. So moving ahead, so we got our sodium bicarbonate, baking soda. Now if we are you can say the sodium bicarbonate, baking soda, obviously it is used in the food items also. So when we use this during cooking, so what is going to happen? Sodium bicarbonate can decompose. So it's solid. So it's going to form sodium carbonate, soda ash, commonly called as water, and carbon dioxide in the liquid form. This is in the gaseous form. So now this is the reaction which is taking place during cooking. Now coming to the uses part. Now uses for making baking powder. Now baking powder is a mixture of, you can say, baking soda and some mild edible acid. So we can take an example of tartaric acid. So formula I'm not writing over here. We don't need to complicate the reaction. So let's say if we have our sodium bicarbonate, if we mix it in water, so these H positive ions are going to come from acid, because you cannot, any acid won't ionize unless we don't add water in it. So it will give us this reaction: sodium salt of acid, whatever acid we have taken, water, and carbon dioxide is going to be released. So carbon dioxide released over here is responsible for making bread, cake to rise or to make them soft and spongy. Then we can say as an ingredient for antacid. Antacids are basically what? They neutralizes the excess acid in the stomach and provide relief. So because it's alkaline. Now again you go back to the basics. Why it is alkaline? Because it's, even if it is having replaceable hydrogen, its parent base is NaOH and parent acid is H2CO3. So this is a weak acid and this is a strong base. Then it is used in soda acid, fire extinguisher, so what reaction do we use over there? We use sulfuric acid and we use baking soda, sodium bicarbonate. They chemically react to give us sodium sulfate along with water and carbon dioxide. So when we extinguish fire, there is white color liquid which comes out. So white is sodium sulfate, water will be there, and carbon dioxide will also be there. So all these three products are sprayed through that fire extinguisher that we use in day-to-day basis. Then we go to the next salt. Washing soda. Washing soda is represented by this chemical formula Na2CO3.10H2O. So this is sodium carbonate decahydrate. Commonly we call it as washing soda. So this again we are going to discuss about the commercial method only. So how do we obtain? So this is manufactured by solvent process only. So same reaction we are going to write NaCl. This is the brine solution reacting with carbon dioxide and ammonia, giving us these products, ammonium chloride and sodium bicarbonate. Now the carbon dioxide which is used over here, from where do we obtain it? This we didn't discuss in the previous salt. So we get commercially carbon dioxide from calcium carbonate. So this is also called as limestone. We have discussed this reaction in the chemical reaction in the equations chapter. So commercially we always try to obtain carbon dioxide by this reaction when we heat limestone. We get lime, calcium oxide, which is also called as quicklime, and carbon dioxide. Then we got our sodium bicarbonate. Now what we are going to do with it? So sodium bicarbonate we are going to heat and we are going to get sodium carbonate, anhydrous sodium carbonate, and this is what we call soda ash. Plus water and carbon dioxide. So if we strongly heat it, these are the products we will get. Now next step that we are going to use sodium carbonate and we are going to mix it in water. This is solid, this is liquid. So we are going to make it aqueous. Now after that we have to do multiple crystallization. We are not going to get this product just by doing it once. We have to do crystallization multiple times. So crystallization is nothing but you make saturated solution, then you cool the hot saturated solution and you get crystals out of it, then you filter it out, you dry it, and then finally you get the geometrical shape crystals out of it. So crystallization, you have to repeat this step multiple times, then only we can get our final product, that is sodium carbonate loosely bonded with 10 molecules of water, and this is our washing soda. Now washing soda uses, if we need to discuss, it's a very important, you can say, a chemical substance which is used for making glass, Na2CO3. It's used for making paper, glass, soap and paint industries. It's very much useful over there. So paper, glass, soap and paint industries also. Then it's used for washing clothes. Why not? laundry purposes. Then it is also used for softening hard water. Now this softening hard water requires, like you can say, under this we have multiple methods that we can discuss in later chapter in the inorganic chemistry part. That's very much theoretical, but yes, it can be used. Then sodium carbonate is used in manufacture of detergents also, soaps, detergents. Now then, one more important is for manufacture of borax. So borax is basically very much useful when it comes to, there is a very famous borax bead test also. So borax is Na2B4O7. So boron compounds are very much useful, specifically boric acid, if we say. It's very much useful for your eye drops. It can be used over there. It's a very weak acid. Then for making hyposolution, so hyposolution is Na2S2O3.5 molecules of water. So this is like this borax. If we talk about, we get hydrated one also. This is the non-hydrated one which I have written. So Na2B4O7.10 molecules of water. This is the hydrated one. So we can have that one also. Then moving ahead to water of crystallization. This we have discussed before also. So I'm just going to take some more examples. So water of crystallization is the number of water molecules loosely bounded to one unit of a compound or a salt. So we are going to discuss examples. So we have blue vitriol. Blue vitriol is nothing but CuSO4.5H2O, copper sulfate pentahydrate. It's blue in color. Then we have green vitriol. This we discussed before. So that is FeSO4.7H2O, ferrous sulfate heptahydrate. White vitriol, that is zinc salt. So zinc sulfate heptahydrate, we even call these as isomorphs. So isomorphs are basically what? Salts having same crystalline lattice. Lattice is nothing but the three-dimensional network structure. So if you see it properly, iron is having an oxidation number of +2. Sulfate, you can say the radical is same. Zinc is also having the oxidation number +2, and they both are having 7 molecules of water. Water of crystallization is same. Now one more we can actually add over here is the Epsom salt, MgSO4.7H2O. So magnesium also, oxidation number +2. Then we have gypsum, which we are going to discuss its commercial method of production. Gypsum is calcium sulfate.2H2O, calcium sulfate dihydrate. Then we have Glauber salt. This is also called as mirabilite. This is Na2SO4, sodium sulfate .10H2O, sodium sulfate decahydrate. So these are, you can say, various examples of crystalline salts, not crystalline, sorry, water of crystallization, like hydrated salts I'm talking about. So next salt that we are going to discuss is plaster of Paris. So I don't want to make it a lengthier video, so I'll be stopping over here. So I'll be continuing in the next lecture, plaster of Paris, properties and uses, and various other definitions. So thank you for listening. If you really like this video, it was informative, please share it with your friends, family, and please subscribe my channel, like and share. Thank you so much.